Welcome to Supervised Learning, Making Predictions, part of the Fundamentals of Machine Learning course aimed at training AI practitioners. In this lesson, we'll explore how machines learn from labeled data, where each example includes the correct answer, to make meaningful predictions. You'll see how powerful algorithms like decision trees, linear regression, and support vector machines can transform raw data into actionable insights. Think of supervised learning as teaching a student with flashcards. Once they recognize patterns, they can accurately respond to new, unseen examples. Supervised learning involves training a model on a dataset that includes both inputs, features, and correct outputs, labels. The model discovers patterns linking these inputs to the labels. Later, when presented with new data minus the labels, it tries to predict the correct output. This approach covers two main tasks: regression, predicting continuous values like price, and classification, predicting categories like spam or not spam. Supervised learning is foundational in applications ranging from finance, credit scoring, to healthcare, disease prediction. Within supervised learning, classification deals with discrete categories, like determining if an email is spam or not. In contrast, regression predicts a continuous numerical value, such as forecasting real estate prices. Both rely on labeled examples to teach the model what the correct outputs are. Classification can involve multiple classes, like distinguishing dog breeds, while regression might involve reading stock trends over time. By understanding the difference, you can better select which algorithm fits your problem, whether it's classifying images or predicting tomorrow's temperature. Meet Sarah, a small-scale farmer growing organic produce. She needs to predict her weekly crop yield to manage distribution and avoid waste. Initially, she guesses based on intuition, often leading to shortages or surplus. After logging weather data, soil quality metrics, and past harvest records, Sarah uses a supervised learning model to forecast yield. Labeled examples of weather plus soil conditions arrow yield teach the system to predict future outcomes. Soon, Sarah's deliveries become more consistent, and her customers enjoy fresh produce without running out. Visualize a step-by-step diagram. Collect labeled data, features plus labels. Choose an algorithm, e.g., decision tree. Train the model on historical examples. Validate to measure accuracy. Deploy the model for predictions. Each arrow connects to the next stage, emphasizing the pipeline structure. This flow helps you see how data moves from initial collection to real-world usage. Understanding this life cycle keeps your project on track and makes troubleshooting easier when your model's accuracy dips or the data needs an update. Consider an email spam filter, one of the most common supervised learning examples. The dataset contains thousands of emails labeled spam or not spam. The algorithm analyzes features like certain keywords, suspicious links, or sender reputation. Over time, the model learns patterns that differentiate spam emails from legitimate ones. With each newly labeled email, the model's knowledge refines further. This real-life case shows how supervised learning saves time and frustration by keeping annoying or harmful messages out of our inboxes. Decision trees are like flowcharts guiding you from one decision to another based on answers to feature-related questions. At each node, the algorithm checks something like, is feature X less than 10? If yes, move left. If no, move right, until reaching a leaf node with a prediction. Decision trees are popular for their intuitive structure and ability to handle both classification and regression. However, they can overfit if grown too large. So methods like pruning or combining multiple trees, random forests, help maintain accuracy. Linear regression is a foundational algorithm for predicting continuous values, like sales forecasts or housing prices. It tries to find the best fitting line that maps input features, like square footage or marketing spend, to an output. The model adjusts its slope and intercept to minimize prediction errors across all data points. This simplicity makes linear regression easy to understand and implement, though it can struggle with highly nonlinear relationships. Still, it remains a go-to method for straightforward regression tasks, offering clear interpretability and quick modeling. Support vector machines, SVMs, Aim to find the optimal boundary, or hyperplane, between different classes, maximizing the margin between them. Picture drawing a thick line between two clusters of points in a 2D plot, with each cluster on a different side. SVMs can handle linear and nonlinear problems by using kernel functions. While computationally heavier for massive datasets, they often deliver high accuracy, making them ideal for text classification, image recognition, and other tasks where precision is crucial. For hands-on practice with supervised learning, sites like Kaggle and UCI Machine Learning Repository provide labeled datasets ready for experimentation. You could try predicting house prices, classifying handwritten digits, or detecting fraud. Kaggle's project section offers real-world challenges, often with example code to jumpstart your exploration. These online communities also provide forums and tutorials, making it easier to apply your newfound knowledge in practical ways. Browse through a few datasets, pick one that interests you, and start modeling. A good labeled dataset is crucial. For instance, in a medical diagnosis application, each patient's record arrives with a confirmed diagnosis label. The more representative your data is, the better your model generalizes to real-world cases. This means handling missing values, ensuring class balance, enough positive and negative examples, and properly splitting the data for training and testing. Think of your data set as study material. If it's outdated or limited, the model's predictions will mirror those gaps or biases. Imagine an online subscription service worried about losing customers. They collect user activity logs, billing histories, and support interactions, labeling each user as churned or active. A decision tree or another supervised model identifies which features best predict churn, like how often the user logs in or if they had billing issues. Armed with this insight, the service can intervene early, offering special promotions or tailored support. This proactive approach helps keep customers happy and reduces sudden cancellations. Once your model is trained, assessing its performance is crucial. Classification models often use accuracy, precision, recall, or F1 score, while regression models rely on metrics like mean squared error. Techniques like cross-validation prevent overfitting, and hyperparameter tuning, adjusting settings like maximum tree depth or SVM kernels, helps refine accuracy. Think of it like tuning an instrument to hit the perfect note. This evaluation and tuning cycle ensures your supervised model performs optimally on both training data and real-world scenarios. In this lesson, you learned the essence of supervised learning, training a model using labeled examples to predict future outcomes. We differentiated classification from regression, delved into popular algorithms like decision trees, linear regression, and SVMs, and explored practical scenarios, spam filters, predicting churn, and more. We also discussed the importance of quality datasets, plus evaluation and tuning methods to maximize performance. These foundational elements prepare you to tackle a wide range of machine learning problems that rely on labeled data. Supervised learning powers countless services, detecting fraud in banking, recommending shows on streaming platforms, and forecasting sales for small businesses. By mastering the art of teaching models with labeled data, you unlock the potential to solve real-world challenges more efficiently and accurately. Better predictions reduce waste, smarter classifications address threats quickly, and personalization drives customer satisfaction. With this knowledge in your AI toolkit, you're ready to deepen your exploration of machine learning. Congratulations, and see you in the next lesson.